Hello, thanks for the introduction. As per the introduction, my name is Jessica Wert, representing a project that was done by myself, Angelica, Estrada, and Oumayma Koulouh from Smith College under the mentorship of Dr. R. Jordan Krauser. And in this project, we aimed to better predict the river flow rate in the Mono River at the Nangbeto Dam in Togo. So why is this important? Every year, the Red Cross spends time and money to help populations affected by floods in Togo. The unpredictable nature of flooding makes it pretty difficult for the Red Cross to identify both when and where to distribute resources prior to the flooding event. And as a result, even more time and even more money is spent to distribute these resources after the infrastructure has already been impacted, such as road closures. The Red Cross was able to provide us with data to help the organization better predict flooding in the Nangbeto Dam. Prior to this project, they had some model that provided little success for this, and so they had requested that we help them out. So if we look at flooding, we know that this is caused by a number of factors. One would be the flow rate of the water coming into the dammed area, and then the pre-existing water level at the dam. The water level at the dam is very easy to measure pretty simply, but the flow rate is a little bit more complicated. And so we targeted predicting for the flow rate so that then it could be combined with the height of the water in the dam already to have a model that would predict for flooding. And so that's what we aimed to do. The data that we were provided with was volunteer collected precipitation measurements from the 8 locations shown on the map on the right. And these are all along the Mono River in Togo. We also had a flow rate measurement from the Nangbeto Dam, which is the southernmost point on that map. And each of these sets of measurements had measurements recorded from August 13th, 2012 to December 31st, 2015. And so I want to take a moment to take a pause to note that there is very clear seasonality in this data. So on the left-hand side, we have plots for each of the precipitation at the locations and then the flow plotted alongside that as well. And so we have clear seasonality here as we have like spikes in both the precipitation and flow at regular intervals. And upon closer examination of the data, we see that those intervals are occurring annually. The spikes are occurring mostly during the month of September. And so with these observations, we went forth into approaching our data. So we were provided with the precipitation from these 8 locations and the flow rate at the dam at this one location. And we were looking to create additional variables that we can have a model that predicts the flow rate even better. And so for that, we added in a dummy variable for location. We added in precipitation lags for the 14 days preceding the day that we're predicting for. We added 1 flow rate lag, and we added some seasonality seasonality variables, indicating if it was in a rainy season or not a rainy season. We added in a month variable, and we added in a variable to indicate if it was September or not. For the measurements of these data. And so with these, we have this initial set of all of these variables and all of this great data. And so we chose a Lasso model because we realized that the goal of this project is to be able to provide a really interpretable and high performance model. And so because we knew that it wouldn't necessarily be statisticians working with this model in the future, the Lasso model provides a more parsimonious solution than other models. And so with this, we trained kind of 2 different models in this. And so the first model that we trained, because we only had 2.5 years worth of data, trained on the entirety of the set. And model 2 trained from the years 2012 to 2014 and tested on 2015. And so we recognize that with such annual seasonality, it would be ideal to be able to train and test on infinite amounts of data, as I think is always the case. But with this limited bit, we wanted to kind of compare the different models that were presented from each of these different options. And so if we go ahead and look, we see that so previously we had removed some of the variables with the lowest coefficients as they correlated to, or they contributed less to the model. And so we were able to kind of like chip away to a more parsimonious model and to a high performing model. And so for each of these models, we have the same coefficients being the initial precipitation lag all the way through 7 days out, the singular flow rate lag, the season variable, and also if it's in September, that little indicator there as well. And so if we go through and look at the coefficients, they are pretty similar across the models. We do see some differences, particularly in like some of these lags here. And so let's look and see how these models performed. So the first model, which was, again, the one that was just trained on the entirety of the data, we don't have a test mean squared error for that because we weren't able to test on separate data. But we got a model that performed with 87.87 R squared value, and it yielded a training mean squared error of 1,520.8. And so we see that it's able to pretty well predict even for the jumps in measurements. And so in this plot, the model is the red and the measured values are in black. We do see a few times like here and here and here and down here when it doesn't predict quite perfectly, but it still indicates a spike just to a different magnitude. And then model 2, the second model that we trained, it yielded a higher R squared value of 88.02% with a test mean squared error of 734.5. And so this is the test, how it performed on the testing set here. And so we see a little bit better performance when it comes to the peaks. We see a little, it's lacking a little bit when it comes to these data points down here. But overall, it's able to pretty well predict for the flow rate of the water at the Nangbeto Dam for the next day. So side-by-side comparison, snapshot comparison of these models, we see that model 2, even though it was trained with less data, it indicates a stronger performance through the R squared value, because that's really the only metric that we can compare across these sets. And so that was the model that we ultimately decided to turn in on this project. Some reflections. It was such an honor to be able to work on this project alongside Oumayma and Angelica. It was really great to kind of have this hands-on experience working with all of this data. And I wanted to give a brief recap of the project as well. We selected the Lasso model for its interpretability and its parsimonious nature. And in the future, what we'd like to do would be to ideally train on much more data to have an even better model. But with limited data, what we were thinking about doing would be to kind of model the time series of the precipitation and the flow rate. So kind of create a model of the data to then feed into this model that we trained for the flow rate. And so we're thinking maybe an Oumayma model would be neat to do that. And essentially what that would enable us to do would be to predict for not only the next day, but perhaps with lower confidence, be able to predict for a day that's a few months out. So that would be in the future. And we've all kind of gone our separate ways with different life paths and graduation and whatnot. But this was a really incredible project. And I know I speak for the group in saying that it was an honor to be able to submit this to the US class competition. It's an honor to be able to share this with you all here. And thank you very much for this opportunity. So those are the image sources, and thank you.
Great, thank you for your presentation. The first question we have is from John Green, and he asks, why Togo?
So I kind of want to back up just a second before, or kind of in the process of explaining this. So this was completed for a class project. And our professor was really great in encouraging us to kind of dream big with the data that we were using. And I can speak worlds about Jordan. He's absolutely incredible. And he essentially said, I will reach out to my network and see if anyone has any problems that they want solved. And so there was someone in his network that worked for the Red Cross that had this data set for Togo. And so he was able to provide us with that information, and we took it from there.
All right, excellent. Another question we have is, how do you recommend that other students get involved in applied projects like this?
I think one of the biggest things is just asking, because networks are a really powerful thing, and you never know who might have problems that are really interesting to solve. And everyone's coming to the table with very different expertise. For example, in this project, the three of us were from different majors, just taking this class as it was like a common interest across the three of us. And so I think you just have to be willing to ask and put yourself out there and open it up to your network, because you never know, even if someone's coming from a different discipline, if they're going to have an interesting problem for you to solve.
Thank you. Another question is, what inspired you to work on this project? So in addition to being or having access to this data set, why were you excited to work on it?
I was really excited to work on this because the impact feels quite tangible. And I'm an engineer by training. And so having, I don't know, being able to see that impact is one of the things that motivates me. And so seeing that this project would actually not only be really interesting and work with river data, which I hadn't worked with in a statistics sort of setting before, but it also, it felt like it was helping people. And I think that that's a really powerful feeling.
Right, thank you. We have another question from John K. at Vassar College. Was there a special reason why you chose Lasso model over other models that add penalizations such as ridge, elastic net? Was it just due to time restraints? I'll let you, there's two parts to this question, so that's the first part.
Sure. So we did consider a few different models, but we kind of, as a combination of time and again, looking for a very interpretable model, we were willing to kind of trade off for a little bit of its performance for its interpretability, because we wanted something that would be very user-friendly to the end user.
All right, and then the second part of his question is, and also I see the data you used was a time series data, so maybe an Oumayma model might work better, ARIMA.
Yes, yeah, and so I think I probably mentioned that in the future work. Oumayma models are great for time series, and so I think that it would be really interesting to see if it would be possible to use an Oumayma to kind of have an intermediate step between this data and this Lasso model being an Oumayma model. And so if we were able to kind of model this trend of the flow rate or the precipitation to train this Lasso model, then that would enable us to be able to look farther into the future, even with less confidence. But it would be really neat to be able to extend the predictive value instead of just the next day. So that's a really great point. Thank you for reiterating that.
Thank you. Another question is, which class material best prepares you for this project?
I would say it was the class that we had taken this project, or that we performed this project in. It was an introduction to machine learning. And in it, we kind of spanned a lot of different types of machine learning and did like little sample labs for the different types that we explored. And so I think it was really great to kind of have a snapshot of all these different ones and then be able to really dive into the Lasso model to get a little bit more familiar with it in the nitty-gritty stuff. So again, it was a machine learning class at Smith. I think it's SDS 293. If there are any Smithies out there, I would highly recommend it.
Great, thank you. Another question is, do you see yourself continuing to work on projects like this one in the future?
So I have since moved on to grad school, but I have a passion for continuing to implement statistics and machine learning into my work. And so I'll certainly look to do similar things in the future. I'm currently working on power systems engineering, but there are a few projects on the horizon that do kind of blend the power systems and the machine learning sides of it. So I'm certainly quite excited for that. And I can speak to the rest of the members in the group as well. And I know that they are already pursuing more statistics opportunities as well.
All right, great. Do you see, coming from this project, any opportunities for collaboration? This is a pretty interdisciplinary project, and so yeah, just any opportunities for collaboration with people in other fields in addition to statistics?
For this project in particular?
Either this project or related projects.
Okay. Coming from a liberal arts background, I certainly see the intersection of, I guess, the interdisciplinary nature of any possible project. And so I certainly can imagine the applications of models like this extending to data sets from other countries. You know, I think extending the model too far beyond that, you'd have to create an entirely new model, because I think a lot of this is dependent on the environmental characteristics of Togo as well, like the topography and kind of the weightings that you put to each of the precipitation measurements. So I think kind of the essence of this can be well transferred to a lot of different projects, but this model itself is probably best suited to Togo.
All right, great. Another question we have is, you mentioned that your partners on the project went on to different fields, and how do you think this project has helped them figure out what they want to study?
So I guess when I should say we parted ways in terms of fields, I think I kind of strayed the farthest from math. So I know the one is pursuing, she's looking to, in the future, apply to PhD programs in biostatistics, and the other is currently working on applied math and has a passion for data sciences continuing. So I think it's something that all three of us will continue to seek to incorporate, because, you know, statistics and machine learning, those are all tools that we can use. And the nature of the problems that you can solve with them is vast. So I think even though we're looking for different applications, myself in power systems, and I know Angelica's in biostatistics, and I'm not sure exactly which area is Oumayma's favorite, other than math and econ, but I think we'll kind of all find ways to apply the machine learning in these various fields.